everybody, Mr. Covey here, and today we're going to talk about looking at sequences from a graphical perspective. Like, how do you graph a sequence and what does that mean? So it's kind of just a twist on what we've already been doing. I hope it's not going to be too crazy. First, just to get your brain working, can you take a look at both of these sequences? And can you write a rule for determining the nth term? Okay. As a reminder, you should be thinking, hey, is that sequence arithmetic or geometric? And then grabbing those formulas and writing the rule. Okay, so once you pause, take a couple minutes, try those two problems. Okay, so that's what I got for those two. Let's run through them real quick. So for this one, I looked at it and I said, am I adding something every time or multiplying? And I hope for that one you can kind of figure out, oh, that one you're multiplying by something every time, meaning it's geometric. And that thing that you're multiplying by every time, that common ratio is 2. Grab your formula and just plug in the missing parts. The first term was 1. The common ratio is 2. That's all you need to plug in. All together, I got a formula. Okay. Second one, I looked at it. I said, oh, I'm not multiplying by something every time. I'm adding something. What is that thing that I'm adding? 3. It's called the common difference. I grabbed my formula and I plugged in first term was 2. Common difference was 3. And all together, I get my formula for figuring out the nth term. Again, the purpose of these formulas is you can take these formulas and you can plug in any n that you want. You can plug in 107, you can plug in 24, you can plug in 6. And it will tell you that number in the list. So it'll tell you the 107th number in the list, 107th term in the sequence. So that was just kind of a little review. Now I want to talk about what does it mean to graph a sequence. So when we're talking about graphing a sequence, I want to graph both of these. What it really means is, well, you're making a graph. The important thing is that on the x-axis, you have n's, term numbers. And on the y-axis, you have terms. So basically the idea is, if you look at the first term, what is the first term? What is the second term? What is the third term? What is the fourth term? What is the fifth term? And then on the y-axis, you plot the number that is that term. If that makes sense. So like if you look at this sequence, the first term, let's do a little counting here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say I just count by ones, normal. Okay. The first term is 1. So for an n value of 1, you get out an an of 1. The second term is 2. Again, this one kind of has a weird pattern here, but second term is 2. When you plug in 2 for n, you get out a term 2. Third term is 4. Okay, so when you put in an n of 3, you get out a sub n of 4. The fourth term is 8. When you plug in 4 into here, you'd get out 8. Fifth term would be 16. Right, if I continue this pattern. So when you have your n is 5, you get out 16. Okay, so it'll be like way up there off my graph here. Okay, so if you look at these dots, and again, I'll kind of emphasize them there. Together, they form this sequence. Okay, so I'm just graphing the term number and then the actual term. Okay, let's do this next one here. So again, down here I'm going to put n, here I'm going to put a sub n. For my n's, I'm just going to plot a few numbers. So 1, 2, 3, 4, 5. And I got to pay attention to what the terms are when I decide what to count by for a sub n. So here the terms go from like 2 to 5, and the next one would be 14. So maybe I should count by like 3s, just so I have enough. Like 3, 6, 9, 12, 15. You can count by whatever you want. Okay. All right. So the first term is 2. The second term is 5. The third term is 8. The fourth term is 11. The fifth term is 14. Okay. Cool. So I hope you're looking at these two graphs and you're thinking like, well, first, there's two weird things. First, normally when you make a graph, after you plot all the points, what do? you connect all the points. You're like, oh, you gotta draw the line through them, Mr. Covey. Get on your game. No, you actually don't do that for sequences. And the reason you don't do that for sequences, if you think about what it means to connect the points, when you're connecting 2 points on a graph, what you're saying is, oh, you don't just have to plug in 1 or 2. You could plug in like 1.5 and you get out the thing in between. That's what you're doing when you're making a line. That's not true for sequences, right? There's a first term. The first term is 1. The second term is 2. The third term is 4. The fourth term is 8. There is no 3.5 term. That doesn't make any sense because we're just counting. Okay, so do not connect the points. Say again, do not connect the points. However, the graphs still have shapes. And so if you look at this one on the right first, I hope you can look at that and be like, oh, all the points line up. It's a line. Arithmetic sequences graphically are lines. They're linear. If you look at your formula, there's no exponent. Nope, it's just a line. There's not a square. There's nothing weird. It's not like a log or something. Just a line. Okay? So arithmetic sequences graphically are just lines. Geometric sequences, a little harder to tell here. Again, I'm going to trace it, but then I'm going to untrace it because we're not supposed to trace it. If you look at that graph shape, it's going, it's shooting off to infinity. We've seen graphs like that. I hope that's jumping out at you as an exponential graph. Okay, so geometric sequences graphically are exponential. And if you look at your formula, oh, I got a variable in the exponent right there, and so it makes sense that it's an exponential graph. Okay, so an arithmetic sequence graphically should be a line, but don't connect the points. And a geometric sequence graphically should be exponential, but don't connect the points. Okay. All right, so then another way they could tell you about a, I guess I should say one thing here. Of course, you could write next to these points like 1, 1, 2, 2, 3, 4, 4, 8. And when you're looking at these points, like when you're looking at a point over here, like 4, 11, what it's telling you is the fourth term is 11. Okay, an n value of 4 gives out a term of 11. Okay, so another way they can tell you about a sequence is by just giving you the graph. So I want to do one of these together, then have you guys try one. We'll do another example. It'll be cool. All right, so first it says, hey, determine whether the graph represents an arithmetic sequence or a geometric sequence, or neither. And then write a rule for determining the nth term. Okay, so I'm just going to glance at this graph on the left here, and I'm going to say, oh, look, all those points, they line up. Okay, it's linear, meaning it represents an arithmetic sequence. So right away, because it's a line, I know that's an arithmetic sequence. Now, if I go to write my rule, I have my formula here for arithmetic sequences. I need to figure out what the first term is and what the common difference is. And these will be really easy to figure out. You just got to know how to read these graphs. Okay. Remember, this is telling you the first term is 7. Sweet. Now to figure out the common difference, I have to look at how far apart the terms are. First term is 7, second term is 11, third term is 15, fourth term is 19. How far apart are the terms? They're 4 apart. So the common difference is 4. Boom. I got my formula. Why don't you go ahead and pause and you try the second one here. Okay. Again, at first glance, all of the points line up. It's linear, so it's going to be an arithmetic sequence. First term was 0, second term was 2, third term was 4, fourth term was 6. Meaning common difference was 2, and I got this as my formula for the nth term. Do a little simplifying, and be aware that you might see it simplified without parentheses. So either of those two blue boxes, you know, that's okay or that's okay. Just know that those two things are equivalent. Flip it over here. I'll just left them with you, and then you guys can try the right way. So I'm going to glance at this sequence, and I'm going to say, oh, it's definitely not a line. In fact, it's got that exponential shape. So this is going to be a geometric sequence. trying to write my explicit formula. I'm sorry, my formula for the nth term. And I know the first term is a half. Now let's be careful about finding the common ratio here. First term's a half, second term's 3/2. If you want, you can always take the graph and just write out the terms. You know what I mean? If you're more comfortable looking at it like this. I am. I think this looks more normal. So like, oh, you're talking about this sequence right here. Okay. How do I figure out the common ratio? Well, you can just look at it, and I can tell that that common ratio is 3. But if you are unsure what you're multiplying by, remember you can always do 3/2 divided by a half, or 9/2 divided by 3/2, or 27/2 divided by 9/2, and figure out that the common ratio is 3. Okay. Cool. Got my formula. Done. Don't simplify this. No simplifying. Remember, people make mistakes trying to simplify that formula. There is no simplifying there. Okay. You go ahead and try this one here. Pause the video, give it a try. Okay. So this was geometric again. I know what you're thinking. You're like, wait, I thought the exponential graphs shot up. Remember, it's also possible that they go like that. That is exponential decay. It's going down. Still an exponential graph, so it's still geometric. Okay. First term was 4. Common ratio was a half. Here's my formula for the nth term. Okay. While we're talking about the graphing thing, this is unrelated to the graphing thing. I'm just talking about a different way they could present you with information about a sequence, and they could do it in a table. Again, this is, I hope, not too bad. The second term's -12, third term's 24, fourth term's -48, fifth term's 9. They're presenting you this information in a table instead of listing it out for you, but it's the same information. Okay? Just representing it a different way. Okay, so what they're asking us to do here is just write a rule. Okay, I'll do this first one, I'll let you guys do the next two. Looking at this, looking at these terms, it's not arithmetic. I'm not adding or subtracting the same thing. I am multiplying by the same thing. That thing I'm multiplying by is -2. So when I go to write my formula, I'm like, okay, geometric formula. Uh-oh. I don't know the first term. The problem here is they tell us the second term. Kind of annoying. It's okay. We can totally just solve this. Remember how this works. We've done problems like this before. I need to figure out that first term. That's the missing thing. Well, I'm going to use the fact that the second term is -12. When you plug in 2 for n, you get out -12. 2 for n, you get out -12. I'm going to use that fact to help me solve for the first term so that I can write the proper formula. Okay? Not too bad at all. What's -2 to the, what's 2 minus 1 is 1. What's -2 to the first power? That's just -2. So I got a sub 1 times -2 equals -12. What's the first term? 6. So then I can grab this guy and say, the real formula should look like this. A sub n equals 6 times -2 to the n minus 1. Boom. Okay. I had to do that little side project to solve for the first term, but once I did that, just plug in the formula. You go ahead and pause and try these last two. Okay, so for this one right here, it was geometric. Again, I didn't know the first term, but I knew the common ratio was -3, so I used that fact, and I used the fact that the second term was -21 to figure out that the first term had to have been 7, so I could write my formula. Okay. The last one here, it was arithmetic. Again, I knew my common difference was 8, but I didn't know what the first term was. But I knew that the fourth term was 31. So I plugged that in to help me determine that the first term was 7, coincidence. And then I correct my formula. Okay. All right, thanks for watching, guys. That concludes this video. And the good thing is, that's all the new stuff with sequences. So we're just going to be doing a lot of practice with these ideas. Cool.